All right. So, what we're going to start now thinking about is dependency relationships. And so, if you recall, when we talked about covariance and correlation, I made a big deal out of the fact that correlation does not imply causation. Because there, all we're looking at are how things rise and fall together, but we're not saying that one thing is necessarily predicting the other thing. But now we're going to start setting up models where we are going to try to predict something based upon the value of something else. And so dependency type relationships, a lot of times they just make logical sense. Like, the amount of nitrogen available to a plant might influence the number of fruits that it can set. And so that would be a cause and effect relationship. And we might be interested in developing some sort of a model that if we knew the amount of nitrogen available, perhaps we could predict what the seed set could be. And again, it could be any kind of a predictive model that you might be interested in thinking about. And so when thinking about, as we're going to start developing these models, we're going to have what we'll refer to as an independent and a dependent variable. So there'll be something that directionally affects something else, but that something else does not directionally affect the predictor. So going back to our example with the amount of nitrogen in fruit set, you could manipulate or understand the amount of fruit set and then, understand the amount of nitrogen and predict fruit set, but you wouldn't necessarily assume that you could modify the amount of nitrogen by modifying fruit set. So fruit set is dependent upon nitrogen. Nitrogen is not dependent upon the fruit set. Okay. And so an important thing that we want to at least keep in mind when we're setting up these dependency relationships is when we played around with covariance between, say, X and Y, we allowed that uncertainty and that variation to be both up and down on the y-axis or left and right on the x-axis. We allowed both of those types of uncertainty to exist. When we're going to model things in a dependency type relationship, we are going to assume that we are measuring our value for the predictor for the x-axis here. We are going to assume that we are measuring that without any error, that we know the actual value. So if we're doing nitrogen and fruit set, we are assuming that we know exactly how much nitrogen was available to the plant. Now, whether or not that's 100% always true, of course it's not. But hopefully we're close enough that we can make that assumption for the sake of modeling. And so I keep saying modeling because it sounds cool, sounds fancy. So what are we going to be doing? We are going to be making what are referred to as linear models. And so the word linear model kind of implies that we are going to be modeling it in such a way that there's kind of going to be a straight line relationship between a predictor variable and a response variable. And although often that is the case, that we are going to be putting a straight line through it, that is not by definition what we're going to mean by a linear model. In a statistical sense, a linear model means something very, very specific. It means that it's a model where no parameter is going to be multiplied by another parameter, and no parameter is going to be serving as an exponent to another parameter. So basically, parameters will never be involved in anything that resembles multiplication with each other. They will be involved with multiplication with other things, but never with another parameter. And that is the definition of what a linear model is. It's not necessarily that it's a straight line, okay? Because we can make linear models that do not predict a straight line, and they're still linear models. Why? No parameter is multiplied by another parameter, and no parameter serves as an exponent to another parameter. And so in a general framework, how we're going to set that up is there's something that we want to predict. And so we could call that our response variable. And that response variable is going to be predicted by the parameters in our model. So let's call that just a model. And what we'll refer to as the error. Now, the error kind of implies that it's a mistake, that there's something wrong, and that is not what we're going to mean here. The error is also referred to at times as the residual. So we can think about the error or the residual as being the leftover variation. So we have our response variable, something that we're trying to predict. We'll have our model, which we will be doing our best to try to predict something with. But our model is never going to be 100% accurate and explain everything. So there's going to be some variation that's out there that the model is unable to capture, and that's what is going to be in our error term. Okay. For the types of models that we're going to be starting with, we are going to assume the important assumption being that our leftover variation, our error variation, is going to be normally distributed. Okay. And so the types of models that we are going to be developing are going to be called general linear models. So they are called general linear models because they are a model. That's why they're called a model, because they are a model. They are called linear. Why? Because no parameter is multiplied by another parameter, and no parameter serves as an exponent to another parameter. And then they are called general. Why? Because they are pretty general. How's that for helpful? Because they can accept both continuous predictors in the model, they can accept categorical predictors in the model, and they can accept a combination of those in the model. And that's why they're called general linear models. Okay. Just to prevent any confusion before we go over it, there is a different type of a linear model that we will talk about near the end of the semester called a generalized linear model. And they differ in that they allow for different types of error structures. And we'll revisit that. It's very unfortunate that there are general linear models and then there are generalized linear models because they kind of sound similar to one another. But we'll revisit those. For now, we're going to be dealing with a general linear model, and we are going to be trying to estimate parameters for that general linear model. So in a more formal framework, let's just think about what that might look like. We're trying to predict something, and that thing that we're trying to predict, that ith value of y, is going to be based upon some linear combination of parameters. And so a very easy one that we can think about is one where we have an intercept and a slope. Okay, it's a very basic, very easy model to think about. You know, this is y equals mx plus b. This is like, you know, whatever it is. I don't know, what is it? 8th grade, 7th grade? Math? I don't know. But it's a line equation. And this is an example of a very simple model. Here's our parameters, the intercept and the slope, beta naught and beta 1. And what we're going to be doing is we're going to be estimating that. So just like with the same rules where mu was a parameter and y bar was our statistic, it was our estimate of it, we are going to have estimates of the intercept and the slope. And they are often shown as the letter B. Okay, these will be our estimate of the true population intercept and the true population slope that we can never know. All we can do is estimate it. And so there's two different ways that we could go about estimating these parameters in the model. The first way is the way that we will be doing it, and it's called ordinary least squares, or OLS. The other way that we could estimate the parameters is to use maximum likelihood. And although maximum likelihood undoubtedly sounds fancier, we have already talked about one of the problems with maximum likelihood estimation is that your observed data are going to be closer to your parameter estimates based upon that data than to the true population parameter values. And as a consequence, maximum likelihood tends to be biased. Ordinary least squares is not biased as long as our data meet the assumptions of the model. And one important assumption of the model is that the leftover variation or the residual variation is normally distributed. And so let's say that we have some data, X and Y, okay? And we're trying to come up with some kind of a model that, predicts Y based upon our value of X. And so again, we're going to try to put this into some type of a model where Y is going to equal an intercept plus a slope times a value of X. And, I'll write this down one last time. Error. Error is always implied. We don't estimate the error. The error is given to us by how poorly or unpoorly our model performs. And so this is the basics of the model that we're interested in. And so how do we go about estimating these parameters? So we can start with estimating the slope. Okay, so again, the slope will tell us the angle at which the line will go when it's going around our data or near our data. And so what we can do to calculate then the slope is it's simply the covariance of X and Y divided by the variance of X. And if we do that, that is going to give us an estimate of our slope. Okay. Once we have our estimate of the slope, so we know the line, we know gravity works, we know that the line has a particular slope. Now we're trying to figure out where the intercept is, so we know exactly where that line falls. Even though we know the angle of it, we don't know exactly where it falls. What we can use to estimate the intercept is the idea that we would expect that line to go through the average of X and the average of Y. Okay? That mythical perfectly average thing, that's where we expect that line to go through. So what we could do is we could solve for the intercept by saying the mean of Y equals the intercept plus our slope, which we have now, times the mean of X. And so all we have to do is calculate the mean of X and the mean of Y, and then just do a little bit of arithmetic, right? So we want to solve for the intercept. And so I'll take the mean of Y minus the slope times the mean of X. And that's going to give me my estimate for the intercept. And now I will have the beautiful line that will describe in a picture form what my data actually look like in the framework of my model. And so so let's just do this in R. That is basically it as a straight up linear model. Oh, one little caveat. So this type of a model is often what is generally referred to as a simple linear regression. A linear regression is a general linear model. Okay. A multiple regression is a general linear model. An ANOVA is a general linear model. An ANCOVA is a general linear model. So there's a long history of kind of confusing the modeling approach that we're using with the actual design of the study. And so, yes, it is not wrong to say that this is a simple linear regression. But as we'll see, there's no difference between what we just did here right now to anything else that is a general linear model. So a factorial ANOVA, same thing. Okay? They're all general linear models. That's all we want to keep in mind. So when people say things like, oh, that's a simple linear regression, or it's an ANCOVA, or whatever they might decide to describe it as, that's really describing the design of the study. It's not anything particular to the statistical analysis, because they are all general linear models. And now we know how to calculate the slope and the intercept. And so now we can learn something about how well our model behaves. So let's jump into R and see what things look like. I think think it's going to be exciting. It's going to be good stuff. Real good. And there's our pretend data that we're going to play with. And it looks to me like we want to try to predict the height of a plant based upon the amount of nitrogen available in its growth medium. At least that's the story I'm telling, so I hope you believe me. Okay, so we got our data. We've measured the height in centimeters, and we have kept track of the nitrogen that was available in the soil. And so again, if we were to have, read this in off of like a CSV, it would look something like that. This is what the raw data would look like, and it's like, okay, cool, let's figure that out. And so again, we could start by, let's just plotting out the data, have a look-see, shall we? So let's plot on the x-axis, I would really like nitrogen, and on the y-axis, I would really like height in centimeters. And here we have it. And there's our data. And again, our goal here is going to be, we want to stick some kind of a line through this, right? And yes, it's going to be a line, but that's not why we're calling it a linear model. Let's never forget that. It's a linear model because no parameters are multiplied by other parameters or serve as an exponent to another parameter. Right. Okay, so how are we going to do that? What we could do is we could estimate the slope by taking the covariance of xy divided by the variance of x. So I'm going to just go ahead and I'm going to do that. I'm going to call up the slope, and it's going to be the covariance of what? It's going to be the covariance of both of those things. Copy, paste, divided by the variance of our predictor, and our predictor is nitrogen. And so now we have our slope, and it is 0.9175621. Again, that's our slope. It's rise over run. And if you think about the units that the covariance was in, nitrogen parts per million height centimeter units, and the variance was in nitrogen parts per million squared units. And so what we're going to end up with after we do that arithmetic is simply 0.917 height centimeter over nitrogen parts per million. And so what that's telling me is that right now, based upon our slope estimate, is that since it's rise over run, every time I increase the amount of nitrogen by 1 part per million, I would expect to increase the height of the plant by 0.917 centimeters. And that is what that slope is telling me. So the next thing that we're going to want, though, is we're going to need an intercept, because we want to make a predictive model. And right now, we have a nice relationship between the height and nitrogen parts per million. But without the intercept, we can't actually predict what the value would be. I couldn't say, well, what do you think that the height should be if I had exactly 8 parts per million of nitrogen? In order to use the model to have an answer to that, I would need to know what the intercept is. So let's go ahead and let's solve for the intercept. So again, the intercept, and I'm going to go back to that little piece of math right there that we did on the whiteboard, the old whiteboard. I'm going to say that the intercept is what? It's going to be the mean of my height in centimeters minus the slope times the nitrogen in parts per million. That should all work. Yes, it should. And oops, nope. This is the problem when there's nobody in a classroom saying, Jim, no, you screwed up. There, now we're better. Okay, 10.66265, that is my intercept. And my slope is 0.917. Okay. There's an easier way to do this, and obviously you would probably not be doing this by hand. And actually, when we get to more complex models, the math actually gets really difficult to do it by hand. So we're not going to do it by hand. We can use the built-in functions in R, it being a statistical programming language, and we can make our linear model in R. So I'm going to create an object called mod, which stands for model. And that model is going to be what? It's going to be a linear model. So the function is going to be LM. And then what? I'm trying to predict what? I'm trying to predict height in centimeters as being some function of nitrogen. Okay. And so this is how we are going to put models into that linear modeling function. We are going to say the height in centimeters. We're going to use this little tilde, which means some function of. So the height in centimeters is some function of the amount of nitrogen in parts per million. So I go ahead and I do that, and I'll look at that object now that we just created. And there's the intercept, which is the same intercept that we got when we calculated it by hand. And then here is our slope, which is the same value we got when we did it by hand. And there's our linear model. So now we have a model where in principle we should be able to predict what the value would be. And so what did I say? For example, at 8 parts per million, if I wanted to estimate what that height should be, well, it would be that plus that times 8. So I would expect that the plant should be 18.0035 centimeters if there was exactly 8 parts per million of nitrogen available. Okay, so that's how we're already using our model now in a predictive framework. So this object that we've created called mod actually has a lot of good stuff in it. A lot more than just the intercept. And not that there's anything wrong with our intercept and our slope. I think it's wonderful too. But there's more information in there. And I'm going to say names mod because it turns out that mod is actually a list. And there's all kinds of stuff that are in here. Let's just think about some important ones for our purposes right now. Well, mod $ coefficients, that's our intercept and that's our slope. That is definitely important. The next thing that we can think about as being important are our residuals. And the residuals, I'm going to make a little graph here to show you what those residuals are looking like. Let's do it. Let's do it. Let's do it. There it is. The residuals, well, let me slow down, Greyhound. Okay, so here's our regression line, and here's all of our observed data. The residuals are simply the distance of our observed data from those points that are on the line, because that is our expected value. We expect, get that out of my face, we expect that all, like when we had, for example, whatever this is at, 7.4, we would expect that much. But what we actually observed was that much. And so this is the error. This is the part of the variation that our model is unable to explain. And that's why it's often referred to as the residuals. It's actually called the residuals in R. It likes to call them residuals because it's the leftover variation. And so if we were to look at the residuals, I could say mod $residuals. These are the values across all of our data for what the residuals look like. And now again, we can go ahead. These red dots here are our predicted values. The white dots are our observed values. So you can see some of these are really close, like up here in the upper right-hand corner. That one's really close, the observed and the predicted. But over here, that one's quite a ways away from here, okay? And all we're doing with the residuals then is just those distances from our observed to our expected. That is the leftover variation. So another thing that's in the model are the fitted values. And the fitted values are these red dots that I drew on here. Okay, those are the predicted values given our model parameters. Okay, and so again, if we knew that, you know, here 8.26 is the first value for nitrogen, that data that we had, and if we were to pop that into, I need that really badly, copy, paste. Okay, so if I were to say that plus that times 8.26, that is the fitted or predicted value for the height for this first individual. And of course it won't ever be perfectly that. That first individual is 17.7, whereas here we had 18.24 as being our predicted value. The difference between those two is the residual or the leftover variation. And if we went back up, there's our residuals, 0.54 away, 0.54 away. Okay. Yeah, I guess I could have, should have. I guess I could have, should have. If I put 17.7 in front of here, 17.7 minus that. There, now we get the negative 5.4, which is actually the same as, whoa, what we got when we looked at the residuals. There's where that value comes from with residuals. And so that is all of our leftover information. And that's going to be really important because what we're ultimately going to want to be able to do is think about how much variation is our model actually explaining. And so before we start building these models, and really if we're going to do a linear model where we have a continuous predictor and a continuous response variable, we probably would like to look at those data to see whether or not we think that they're somewhat normally distributed, because again, we are going to be modeling our data as being random variables drawn from a normal distribution, so it would be good to know whether or not we're even remotely normal. But then once we've done the model, the next thing that we can do is we could look at the distribution of the residuals, because the residuals should also be normally distributed. And so I could go ahead and I could make a histogram of those residuals. And then I'm like, well, you know, this is what happens when you only have 10 data points and you're trying to make a residual for them. But we could be extra cautious, perhaps, and use the normal test as a guide, just to see whether or not we're happy thinking about this as being a normal. And I'm going to just go ahead and run that. Shapiro-Wilk test, here's the p-value. We would not reject the null under those situations, so we feel pretty good saying that our data are random variables drawn from a normal distribution. Now, we only have 10 observations, so we don't really have all that much flexibility to really test for normality. For example, if I were to use my favorite one, which is the D'Agostino test for the normal test, we can't even do that because you need to have a sample size of at least 20. Okay, and so it's just something to get into the habit of, and we'll talk more about quality control in a little bit. But we expect our residuals to be somewhat normal. What we will find, especially when we start having more than one predictor, is that it's often easier to interpret the parameter estimates of these models if we are looking at what are referred to as the standardized beta coefficients, or the standardized parameters. And as you might guess, that means that we are going to put them into units of standard deviations, because it's going to be easier to interpret, because we won't be trapped in the units. You know, maybe I don't know what a centimeter is. So I would get very confused if I were to look at a slope of 0.9176 if I had no idea what a centimeter was, or if I had no idea what a parts per million meant, because it's going to be, you know, dependent upon those. But if we were to z-transform the data, then we could get what are referred to as standardized coefficients. So I'm going to say scale, and I will say scale. And now I'm in units of standard deviation. So now the slope is, it's what? 0.68. And so that means that I would expect the height of the plant to increase by 0.68 standard deviations every time I increase the nitrogen by 1 standard deviation. And by having it in units of standard deviations, it wouldn't have mattered had I had the height in inches and the nitrogen in moles, or whatever it might be. It wouldn't matter, because now it's going to be in units of standard deviation, and we're no longer going to be under the control of whatever units we tended to measure them by. And so that's another thing that we can do. There's a shortcut to getting these z transformed, or these standardized beta coefficients. There is a library called lm.beta. And then within there is a function called lm.beta. So I'm going to go back up here, and now my model is in the units, the raw units. And if I were to use that function called lm.beta and put my model in there, there I'm getting the scaled coefficients. And so again, here is my slope, 0.682. This is what we got here when we scaled it by hand. And this is giving me 0, which is the correct answer, because if everything is centered at 0, the intercept must be at 0. And here we see the computer working really hard, but not quite getting there with the whole rounding problem that computers have. But I'm going to say that 7.1 times 10 to the negative 16th is probably close enough to 0 to feel good about the fact that it's 0. Okay, and so let's go back and look at our figure again, or at our data plot. Okay, so here we have that. We have this object called mod, right? And so we could draw the regression line through here by using that abline function. So I know that we've been playing with abline. The reason why it's called abline is that it's actually not called abline. It's called AB line. A is the intercept, B is the slope, line is a line. And so if we use the abline function, we can just go ahead and throw mod in there. And it will know what to do with it. And there it is. There is the model that we have generated, and we've nicely plotted it out with our raw data. Okay, so we got a model. We have a slope estimate for the model. We feel pretty good about our model. I will say this repeatedly throughout the semester. You gotta love your model. Gotta love your model. It's a really important thing to love your model. And now what we might be interested in doing is figuring out how much variation is our model explaining? Because again, we already talked about, we know what the residuals are, right? The residuals are, these are all the variation that we're not able to explain with our model. And so what we'd like to know is, well, how much are we actually able to explain? And so for this, we have to calculate a couple of different, what are referred to as sums of squares. And so the first one that we would need to think about is the sums of squares associated with our model. And the sums of squares associated with our model is going to be the distance between our predicted values and the mean of our response variable. So let me make a little plot to show you what the heck Jim is talking about. That would be helpful, undoubtedly. So that blue line right there, that is the mean height in centimeters. These are obviously all of our data. And then there is our regression line, right? And so the sums of squares for the model will be the distance from the predicted values, those points that are on the regression line, to the mean of the height in centimeters. And so we can go ahead and say, wait, nope, not yet, we can't. There we go. And so these red dots here, those are our predicted values according to our model. And then what we would take are the distance from all of those predicted values to the mean. That is going to be the sums of squares associated with our model. And so we can call that the sums of squares of our model or the sums of squares of the regression. All right, so we got that. And I'm going to go ahead and do that, and all the code is on there, so we don't need to go through the cumbersome part of the code. But we got that number right there. I can even watch what I can do. Right there. Sweet. That was high tech. So that's our sums of squares. I'm going to write it down so we can keep track of it as soon as I find Powell. All right, so we're going to have our sums of squares, and we'll say the sums of squares of our model is what? What did I say it was? What the heck? 7. I was so proud of it. Now I don't remember it. 7.46. Close enough. Okay, I'm not going to even bother rounding. That's how I'm rolling. Okay, next we're going to want to think about the sums of squares of the error. And this should look familiar because we've already talked about what the residuals are. And what we're going to do is we're going to take the sums of the squared distances between our observed value and our predicted value. So again, this is the part of the variation that our model is not capturing. Our model is capturing the variation from the grand mean to our predicted values, but it's not capturing this other portion of the variation, which we call the error term. So all we're going to do is we're going to take our observed value versus our expected value according to our model. We're going to take that difference, we're going to square it, and we're going to sum up all of those. And that's going to give us the sums of squares associated with the error or the residual. And so I will go ahead and I will just simply do that using the code that we all have. And what do I get? I get 8.57. Sure, 8.57. I'm really against rounding appropriately today, apparently. All right, so we got our model sums of squares. We have our error sums of squares. And now the final thing that we're going to need to calculate is the total sums of squares. And so the total sums of squares, there's two ways that we could do that. I'll even zoom in on me a little bit. One way that we could come up with the total sums of squares is to simply add these two numbers together. And what is that? I will do that really quickly here. 16.045. Okay. So the sums of squares are additive. Here's the sums of squares of our model. Here's the sums of squares of the error term. And here's the total sums of squares of our model. The other way that we could estimate the total sums of squares would be to take all of our values of y minus the mean value of y squared and take the sum of that. And that would be our total sums of squares. Now this should look kind of familiar because this is the numerator for variance. Remember? That's how we calculate the variance. But now, I don't care about the variance. I just care about the sums of squares, darn it. So that's all I care about. If I were to do that, yi minus y bar squared for all of those, that is the answer I would get, 16.05, because there's two different ways in which we can calculate the total sums of squares. Again, you could just simply add together the model sums of squares and the error sums of squares, or you could go ahead and do the arithmetic and do the basically the numerator of the variance when you're calculating the variance. And so we go ahead and we do that. We got 16.45, so that's great. So now we got all these things, and again, we can point out what are we doing actually. That's the sums of squares total. There's our observed values. That blue line again is the mean of y. And so all we're doing is we're taking all those deviations, we're squaring them, and we're summing them up, and the answer to that is 16.045. And so if we wanted to now know how much of the variation of our data is our model actually describing, right? So let's go back and let's plot our actual real data again. Plot the x-axis is nitrogen, the y-axis is height. Did I say height? I didn't mean to. Let's see here. There's our thing. And then I will say ab line, our model. Okay, so there's our beautiful model. We're really proud of it. And we would like to say, well, you know, how much variation is our model actually explaining? We know it can't explain 100%. Mathematically, it would blow up if we actually had it in such a way that we explained 100% of the variation. But we'd like to know, well, how much variation are we explaining? So what we would do to calculate that is we would think about the sums of squares associated with our model, okay, divided by the total sums of squares. And that will give us the proportion of variation that is explained by the parameters in our model. And so what do we have? We had the, what did I call that? Sums of squares regression. Okay, so the sums of squares regression divided by the sums of squares total is 0.465. So we're explaining 47% of the variation in height with our model, where our only predictor is the amount of nitrogen. So that's pretty good. We're explaining just shy of 50% of all the variation in height by this very simple linear model that we've put together. So this sums of squares of the model or the regression divided by the sums of squares total is what's referred to as the coefficient of determination. Yes, the coefficient of determination, also referred to as the R squared. And this is what the R squared of the model is. Technically, we refer to it as the coefficient of determination. Casually, we refer to it as the R squared. So an interesting thing is, why is it called the R squared? Well, there's a good reason. Because it is actually the square of the correlation between our fitted values and our observed values. Okay, so we have our fitted values, and our fitted values, if you recall, they're in that object mod. So if I want mod $fitted, right, there's the fitted values. Those are the values that are actually on that little red line there. So let's call it, I'm going to call it fitted, sure. And it's going to be mod fitted values. Copy, paste. And then we have our observed values, which we already have, which I am calling height. But I'm going to just be explicit and rename a new object. So now I have my fitted versus observed. If I were to look at the correlation between fitted and observed, I get 0.682. If I were to square that, I get 0.465, which is the exact same thing I got when I divided the sums of squares of the regression divided by the total sums of squares. And so that is why it's called the R squared, because it actually is the square of a correlation coefficient, but it's the correlation between our fitted values and our observed values. And that is the coefficient of determination. So now, so great, we can sit back, and I feel pretty good about our model. You know, that looks pretty nice, I think. I pointed that way and looked that way. We have a model now. We have estimated a slope. We have estimated an intercept. We have the amount of variation that our model is explaining. So the next thing that we're going to want to think about is a little bit of hypothesis testing, maybe, or not. I'm pretty happy with this model. I'd be happy to walk home and feel like we've done something good here, but invariably somebody's going to want us to do some hypothesis testing. So we'll do that. Take a little break, but then we'll do that.